All right, so here we get started on our next section. This is 4.8. This is solving trigonometric equations with identities, page 272 of your workbook. And here we go. So this is the culmination of what we've been doing for the last few lessons, everything that we've been doing with trig identities. Earlier, what we were doing was we started off by verifying trig identities, showing that, well, it's true for this value of x or theta. And then we launched into doing a full trigonometric proof, which we would show that this mathematical beast is equal to that mathematical beast always for any value of x or for theta. And that ended up being a trig proof. Now what we're going to do is we're going to solve equations using these facts. And we're going to use this big toolkit that we have been developing now. We have lots of different things that we can use. We have lots of different equations that are, and formulas that we know that we can use in here to now solve equations. So a few reminders that it tells us about. It says factoring is our friend. Always, always, always look for common factoring as a first step. We'll often be doing trinomial factoring in here as well. And so that's the first thing that we're going to be looking for. It tells us something important happens when we take a square root. When we take a square root, we will of course have, we're going to have plus or minus when we take the square root of both sides of an equation. We'll have to look for that. If you're factoring a trinomial, one side better be equal to 0. It doesn't really make much sense to talk about x squared plus 3x is equal to 7. And so now let's factor that left side and get x plus 3 equals to 7. That doesn't really tell us anything. We need it to be equal to 0 for it to be something that's meaningful here. Watch your domain. So we will have restrictions that will often give extraneous solutions. These sorts of things. Never divide out your functions when you're solving the equation. So when we will have examples of each of these as we go along. And then restrictions, of course, you should always state them whether you're asked to or not, and watch for extraneous or phantom solutions happening because of our restrictions. We can sometimes tell that old solutions actually aren't part of what we're trying to look for here. Okay, so moving forward, we start off with this, and there's going to be clues sprinkled in these questions of what we need to do. It asks us to do this within a specified domain, so make sure that we're adhering to that domain. That domain, in this case, we have 0 is less than theta is less or equal to 2 pi. So that tells us that we're going to be answering this in radians, not in degrees, but watch for that. The standard one with when one full revolution is 0 less than theta is less than 2 pi. Be careful that this symbol is less than or equal to, because if it's just a strictly less than symbol and 2 pi is one of your answers, it's no longer in the domain of what we're looking for. All right, so let's move ahead with this. This starts off with the fact that cos 2 theta plus cos theta is equal to 0. Now, it's not ready to go with factoring or doing anything with combining those yet. Remember that cos 2 theta, it's a double angle identity, and it means something different than cosine theta. We can't combine those together. We can't add them together or do anything with those until we turn them just each into something in terms of cosine of theta. So we need to make sure that that just ends up being theta. Remember, for cosine 2 theta, we had 3 manifestations of what cos 2 theta was equal to. One of them looked like this, cos squared minus sine squared. One of them looked like this, 1 minus sine squared theta. And the third one looked like 2 cos squared theta minus 1. The fact that we've got cosine elsewhere here in this equation and we don't have sines going on tells us that we probably want to use that third manifestation of cosine double angle. And so let's do that. Let's use that third one, and we're going to make that first term equal to 2 cos squared theta minus 1 plus cos theta equals 0. So there's our first step. We've replaced cos 2 theta. Now everything is just in terms of theta. We can now proceed to factor. Our next step, let's probably write this order that we're more used to seeing. Let's make it look like that. All right, from this point, we could do this. We could make a substitution and call it 2x squared plus x minus 1. Some students like to do that to be able to factor it. Be careful when you do that you make it perfectly clear to whoever's reading your work. Let cos theta equal x, and therefore now we state our new trinomial. Then we factor it, and then we substitute it back in. You guys are probably at the point where you can handle doing this factoring with the cosines in here. The fact that 2 cos squared is our first term tells us that one of them is 2 cos theta and the other one is 1 cos theta. Those two multiply to 2 cos squared theta. The fact that the back end multiplied to -1 tells us that they're both going to be 1. One of them is going to be adding, one of them is going to be subtracting. And the fact that they add 2 in the middle, positive 1 cos theta, means on the outsides I have 2 cos theta, positive. On the inside, I have -1 cos theta, and this is how it factors. Our next step now is to find solutions. We break that into 2 micro equations, and we have therefore 2 cos theta minus 1 equals 0. Cos theta is equal to 1/2. Where does that happen? Where is cosine theta equal to 1/2? That happens on our pi thirds in quadrants 1 and 4. So down here and up there. And so theta is equal to pi thirds, and it's equal to 5 pi thirds. From this piece, we have cos theta is equal to -1. That happens here. Theta is equal to, our domain simply is within 1 full revolution, and now we can conclude, therefore, theta is equal to, let's list them all, we put them in order, pi thirds, pi, 5 pi. This question, we don't have any restrictions to deal with or look at, so that's it. Next one, again, we have cosine double angle, cos 2 theta, so right away we want to replace that with something in single theta. And so this ends up being, well, I don't know, which should we use? The fact that it's already factored out. So the 4 sine squared theta minus 3 is going to be separate. We're not going to, it's already factored for us. So we could do this a couple of different ways. We're dealing with sine, so let's continue to deal with sine, I suppose, and let's call this 1 minus 2 sine squared theta. That's what that is replaced with. The other half is 4 sine squared theta minus 3 equals 0. And now we can break it into its micro equations. We have 1 minus 2 sine squared theta equals 0. 2 sine squared theta is equal to 1. Sine theta is equal to, divide both sides by 2, and then square root. But be careful here. We need to, the fact that we're square rooting both sides, we need to have that's plus or minus 1 over 2 square root. Keep in mind, square root of a half is 1 over root 2, and if I rationalize that, denominator, this is equal to root 2 over 2, plus or minus. Some of you prefer the 1 over root 2 form, some of you prefer root 2 halves. You have to be aware that both of those are equivalent. They mean the same thing. They refer to the same angle when we have sine theta equal to that. What we have is the pi quarters in all four quadrants. So theta equals pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Let's just have a look at our domain, and our domain is going from 0 to 2 pi, so those ones are all legit. Second half of this says 4 sine squared theta minus 3 equals 0. Sine squared theta, add 3 to both sides, divide by 4. Sine squared theta is equal to 3/4. Sine theta, square root both top and bottom. We need plus or minus root 3. Square root of 4 is 2. So root 3 halves, okay, we know what that is. We know how to deal with that. If we have sine is equal to that, we are talking about your pi thirds reference angle. It's both plus and minus, so it's not just quadrant 1 and 2, it's also quadrants 3 and 4. And theta equals pi thirds. 2 pi thirds in quadrant 2, quadrant 3, 4 pi thirds, 5 pi thirds is the full list. Therefore, we conclude we're going all the way from 0 to 2 pi. Theta equals pi quarters, pi thirds, 2 pi thirds, 3 pi quarters. Just continue to list them. 5 pi quarters, 4 pi thirds, 5 pi thirds, 7 pi quarters. Holy junk, that's a lot. Not too bad. All right, number 3. All right, the first thing that we have to be aware of is this domain here going from negative pi all the way around to 3 pi. So negative pi means we're looking at quadrant 3 and 4, negative angles, and then going all the way to 3 pi going in a positive direction means we are including all of these, nope, yeah, it is. All these angles going to 2 pi, but we're going to keep going around and we're actually going to go to 3 pi. So we have quadrants 1 and 2 angles from our first and second rotation. We have quadrant 3 and 4 angles from rotating positive and rotating negative ways. So we have to be careful and watch for all of that. All right. On top of that, it looks pretty messy to start with anyway. So on top of that, we've got 2 tan theta cos squared theta plus sine theta tan theta minus 2 tan theta equals 0. Step 1, let's common factor out tan theta. Leaves us with 2 cos squared theta. Sine theta minus 2, close your bracket, equals 0. So tan theta is doing okay out there by itself. We can leave that alone for now. But in this trinomial that we have left, we've got cos squared and we've got sine. We don't really know what to do with that. That would be kind of akin to saying x squared plus y minus 2. And go ahead and factor that. Oh, I don't know what to do. That seems a little odd. I don't know what to do with that. However, we can do stuff with cos squared. The fact that cosine squared, using our Pythagorean identities, cos squared is 1 minus sine squared theta. Make sure that's in brackets because it's multiplied by 2. Sine theta minus 2, close your bracket, equals 0. Holy cow, lots going on in here. Tan theta, just distributing. This ends up being negative 2 sine squared theta. We have plus sine theta. And then the positive 2 from that first term, minus 2, those add to 0. So what's this? I'm going to common factor out sine theta. Now we have tan theta, sine theta, and what we're left behind with is 1 minus 2 sine theta. Not squared because we common factored out sine, equals 0. All right, so what does this give us? Let's change colors here just so it separates this work. We have tan theta equals 0. That happens, of course, and theta is equal to 0 and pi, 2 pi. It's not quite making it to 3 pi, right? It's strictly less than 3 pi, so we're not going to include 3 pi in this list, but we are having to go backwards and have negative pi as a solution in here. So those are your solutions for tan theta. Sine theta equaling 0 actually gives us the same solutions for tan because tangent is sine over cos, and so therefore we have theta equal to the same things, negative pi, 0, pi, 2 pi. Our third piece, 1 minus 2 sine theta equals 0. Sine theta is equal to 1/2. And where does that happen? Sine theta is equal to 1/2. It's here and here. So theta is equal to pi over 6. Also 5 pi over 6. But that's just within the first revolution. Quadrants 3 and 4, sine is not positive, so we'll not have any new answers, but we still have another half a rotation around here because we're going all the way up to 3 pi. So we have 5 pi, 1 pi over 6 and 5 pi over 6. We also have, let's add 12 pi 6 to that, and it gives us 13 pi over 6 and 17 pi over 6. Why did I add 12 pi over 6? Well, because 12 pi over 6 is plus 2 pi. We're just adding one more full revolution, and 2 pi is 12 pi over 6. All right. Let's put this all together. Our solution is theta is equal to. Let's first deal with our restrictions. What can theta not equal? The fact that we have tan theta in our equation means that cos theta can't equal 0. So therefore, theta can't equal pi halves plus n pi, where n is an integer. And let's keep that in mind when we look at our solutions. So therefore, our solution list ends up being just all of these. That list is duplicated right here, but then when we have all of our sine theta is equal to 1/2, all of those, let's account for that too. Going from least to greatest, this starts with negative pi, 0, pi over 6, 5 pi over 6. We have pi. Nothing again until we get around to 2 pi, 13 pi over 6, and 17 pi over 6. Ends up being quite the list, but that is it. Number 4, next page. Sine 2 theta is equal to tan squared minus 1 equals 0. In this question, we're going from 0 to 360 degrees, so we get to work in degrees instead here. Please pay attention to that. Again, this one is factored, and so we don't need to try to factor trinomials or anything like this. We don't multiply this stuff together. We have the fact that sine 2 theta is equal to 0. That's our double angle identity for sine. We only have one of them, we only have that sine 2 theta is equal to 2 sine theta cos theta. And if that's 0, then we break that into microequation. Sine theta is equal to 0, happens at 0, 180 degrees, 60 degrees. You need your degree symbol on that, please. Otherwise, it's assumed to be radians. Here's cos theta equal to 0. Cos theta equals 0 happens at 90 degrees, 70 degrees. Second half of this is tan squared theta minus 1 equals 0. And tan squared theta is equal to positive 1. Square root both sides. Now we have tan theta is equal to plus or minus 1. Remember that tan theta is equal to 1 on the 45s. And it's negative 1, quadrants 2 and 4. All of those together gives me theta is equal to 45 degrees, 135 degrees, 225 degrees, and 315. So we put all that together. Before we start to have our final list of theta, we should state restrictions. Tan theta, which is equal to sine theta over cos theta, is present in our equation. Therefore, cos theta can't equal 0. It's just cosine can't be 0. Sine's okay because tangent isn't in the denominator, tangent's in the numerator, so it's just whatever makes it undefined, which would be cos theta can't be 0. Therefore, theta cannot be 90 degrees plus n times 180 degrees. So this time we're working in degrees for our restrictions. We still say n is an integer, but it can't be 90 degrees plus or minus any multiple of 180 degrees on that. So we have to watch for that, which means these two over here, arc screens. Now we can conclude, therefore, theta is equal to, let's have all of our remaining solutions, 0 degrees, 45 degrees, 135, 180, 225, 315, and 360. Onwards. Steps shown below are used to determine complete solution. Set to the equation of 3 sine squared plus cos squared plus 5 sine x minus 4 equals 0, where theta is between 0 to 2 pi. So this equation looks nasty. The fact that we have sine squareds and we have cos squareds and we have sine x, we could take a couple of different approaches to this. We could convert cos squared into 1 minus 2 or 1 minus sine squared. We could do that. In this case, what was done in this question is this 3 sine squared was just broken apart into 2 sine squared plus sine squared. And the reason that the author of this solution wanted to do that is because they want to group those together, because we know that sine squared plus cos squared is 1. And if sine squared plus cos squared is 1, this now becomes 2 sine squared x plus 1 plus 5 sine x minus 4. So is this grouping, is this breaking apart of 3 sine squared? Is that the same as 2 sine squared plus sine squared? Yes, it is. Once we've done that, can we group the sine squared plus cos squared to equal 1? And here it is. Yes, that's correct. So nothing looks wrong yet. In our next step, just rearranging, combining your +1 and your -4. This looks all good. They've kindly factored for us, and so maybe we should just double check to see if this factoring is correct. Let's multiply this back together. 2 sine squared, when you multiply the front end, the outside is 6 sine, the inside is -1 sine. Those certainly add to 5 sine x, and then -1 times +3 is -3. So this looks legit. This looks really good. We have sine x is equal to 1/2 from this part, and we have sine x equal to -3 from that part. So this looks legit. Everything looks like it's good. It appears to be that they've noticed that we have no solutions from here. That's not giving us an answer because, well, there's no solution to sine x equals -3. Remember that sine x has a range between -1 and +1. And so is it ever equal to -3? Nope. And so sine x equal to 1/2, this looks really good. Pi/6 is where sine x equals to 1/2. So question 4 says, where is our student's first recorded error? There appears to be none, except for the fact that when sine x is 1/2, that's this in quadrant 1, but it's also this in quadrant 2. So sine x is 1/2 has a second solution of 5 pi/6. So in step 6, is the solution. All right. Question number 5. The values of x that satisfy the equation 2 sine squared equals negative sine for the interval -pi to +pi. Okay, so a few things going on in this question. The first thing that I want to mention is this interval notation. Remember that that means -pi less or equal to x, strictly less than pi. So the round bracket on the right side here means that it's strictly less than pi. The square bracket means that it includes the point of -pi. So that's our first thing, is that we have our domain is in interval notation instead of set notation, and we just have to be mindful of that. All right, the first thing that jumps out at me about this, 2 sine squared x is equal to negative sine x. Do not do this. Resist the urge to divide both sides by sine x. You're thinking, that's going to make things easy. That's 2 sine x equals -1. Be careful about that. We can't treat it like that. We can't divide out potential solutions. That's essentially what's happening if you did that step. Instead, let's bring everything over to one side, make it equal to 0. 2 sine squared x plus sine x equals 0. Now we common factor sine x times 2 sine x plus 1 equals 0. From sine x equals 0, we get, those are our solutions. We're going from -pi to +pi. So x equals -pi, 0. It's not quite equal to +pi, right? It's strictly less than pi, so that's going to be it for there, for that half. The other half is 2 sine x plus 1 equals 0. Sine x, subtract 1 from both sides, divide both sides by 2. Sine x equals -1/2. We are dealing with pi/6 in quadrants 3 and 4. And x is equal to -5 pi/6, because we're going backwards, -pi/6. And that's going to be it. Altogether, x equal to -pi, going from left to right. 5 pi over 6, negative pi over 6, and 0. That ends up being our answer, D. And that's it. Now, what would have happened if we had approached this question like this, if we had divided sine squared from both sides and left ourselves with 2 sine x is equal to negative 1, sine x is equal to negative a half, we would have gotten only these solutions. We would have missed those by dividing that stuff away. So be careful not to do that. This is really what we need, is all 4 of those. And there you go. All right, good luck with the practice questions. Let me know if you have any questions.